Welcome everybody to the VacCAP webinar series. My name is Amaya Tucha and I'm a member of the VacCAP team. I will be the webinar's moderators for today. Today we will be discussing high throughput assessment of blueberry fruit internal bruising using deep learning models with Dr. Chengyao Tan. Dr. Tan is a postdoc under the supervision of Dr. Charlie Lee at the University of Florida. His research focuses on applying deep learning techniques to solve computer vision problems in the domain of high throughput phenotyping, such as blueberry fruit internal bruising detection, cotton ball counting, and yield estimation. We're very excited to have Dr. Tang on the topic of today's webinar. I will ask everybody to just please remain muted and with your camera off. If you have any questions, feel free to type it into the Q&A or the chat box, and we will read those questions at the end of the webinar. And so with that, I will just let Dr. Tang to go ahead and start the webinar.
Oh, can you see my screen clear?
Yes.
Okay. Thank you for the warm introduction. Good afternoon, everyone. Today I have the privilege of presenting on behalf of my advisor, Dr. Charlie Lee. And I will be discussing our research on high throughput assessment of blueberry fruit internal bruising using deep learning models. And this project is a collaborative effort with our collaborators from North Carolina State University, Dr. Perkins Vasey, Hideko, and Dr. Bill Rizzo. First of all, I will briefly introduce the background. Nowadays, blueberries are becoming famous. However, those blueberries for fresh market need to be manually harvested because they are easily damaged by machine harvesting. And this video shows the typical machine harvester when the sticks swing back and forth, blueberries fall onto the belt, and this procedure may cause internal bruising. And although the firmer blueberries appear to be more bruise resistant, it is still challenging to accurately estimate the bruising ratio. Additionally, accurate bruising ratio estimation can help breeding programs to determine the cultivars that may be more suitable for machine harvesting. Currently, there are two main methods that can detect blueberry internal bruising. The first is manual inspection. This method is subjective and it relies on expertise of humans, and it is definitely labor intensive. The other method is using machine vision for inspection. Several non-destructive methods using hyperspectral imaging to detect blueberry internal bruising. However, the hyperspectral systems are expensive. Moreover, the system setup is complex and it requires a strict imaging environment. Therefore, we want to develop a high throughput approach that can be used for blueberry internal bruising detection. The objectives of this research are as follows. The first is to build a blueberry impact bruising dataset, and then to train and evaluate deep learning models for blueberry fruit and internal bruising detection. The third is to analyze the bruising ratio across different yields and genotypes. And the last one is to evaluate the correlation between the Young's modulus and the bruising ratio. Next, I will talk about materials and methods. The first is sample preparation, and this part is done by our collaborators, and they helped us collect the blueberries from the research farm from 2021 to 2023, and all the collected blueberries were transported on in coolers, and they were held at 4 degrees Celsius overnight, and then warmed up to 15 degrees, and sorted as firm and fully blue fruits of similar berry size within cultivators. And then we use this berry bruising system to generate those internal bruising, and we select a set of blueberries that were completed blue and firm, and dropped them at a height of 20 centimeters onto a stainless steel pail like this. And the pen was lined with bubble wrap, and we cut a 9 centimeter diameter hole inside, and the blueberry will drop onto the hit the steel once and then bounce onto the bubble wrap to avoid the second-hand collision. And for each cultivator, we selected they dropped 50 bruised berries, and then held them for 18 hours at room temperature in plastic bags. And during this process, they will try to make sure the equator of the blueberry hit on the pen, and then blueberries were cut in half along the equator with single-sided razor blades, and the 2 halves per berry were placed on the white paper. And then they used a digital camera to photograph or cut blueberry samples of each cultivator. And below are 2 example images of 2 cultivators. And the other set of blueberries were divided into 3 replicates, and each replicate contains 10 berries. And they used a TAXT2 texture analyzer equipped with a 2 millimeter flat probe to record the data during the puncture process. And then they calculate the Young's modulus, 20% bruised strength. Next, I will talk about our deep learning-based approach to detect internal bruising, and this figure shows the overall approach. And the first step is to use to train object detection to detect each individual berries in the image. And then we use a segmentation model to segment blueberries from each cropped image to get the mask, the berry area. And the last is to use a blueberry bruising another segmentation model to segment the bruising areas. And then we can calculate the bruising ratio by using the bruising area divided by the berry area. And we select the YOLO model for blueberry detection and segmentation. We select around 200 images like this, and annotate each berry with bounding boxes. And for the segmentation asset, we also selected 200 images of individual fruits and annotate the masks. And then we established the 2 image datasets, and all images within the each dataset were randomly divided into training, validation, and testing datasets by a ratio of 8 to 1 to 1. Additionally, all images for training were augmented 3 times using flipping and 19-degree rotation, because some berries were placed vertically, so we need to rotate the image to enlarge the diversity of the training datasets. Considering the initial internal bruising of blueberries is more diverse compared to the berry segmentation. So we establish a larger dataset that contains about 1,000 images. We also want to know if the model only trained using 2-year data still can be used for the new data. Therefore, we established the 2 image datasets. One contains the images collected in 2021 and 2022. The other one contains all 3-year data. And we did the same split operations as berry datasets. That means we also split dataset to the training, validation, and the testing, and do the augmentation. And below are 2 example images of annotations. The purple part is the bruising, and these are 2 typical bruising area, and the shape is like triangle. Now I will show you some results. First, the table shows the evaluation results on 2 different tasks. The trained models can accurately detect and segment blueberries, because we can see the precision and the recoil is 1, and the MAP 0.5 is very close to 1. And the left figure shows the detection results, and we can see even this vertical placed sample also can be detected correctly. And the right figure shows the segmentation results. And we can see they are also very accurate, even though the shape is not regular. Then this table shows the performance of bruising segmentation use YOLO V8. We tested 2 different segmentation models. The first is YOLO V8 and another is YOLO V11. And first, we can see we also compare the training process with and without transfer learning and data augmentation. It can be seen that the model trained on 3-year data here. This is the best results on 3-year data. Is slightly higher than that of 2 years data. Additionally, the model trained on we can see this row. The model trained on 2 years data still can achieve a good performance on the 23 years data, although it is slightly lower than the model trained on all 3-year data. And for the YOLO V8 seg model, transfer learning and augmentation can help improve the performance on 2-year data. We can see this row. Yeah, the pro-train and augmentation achieved the best performance here. But for the 3-year data, the best model is without transfer learning and augmentation. And I think this is because the density of 3-year is much have more images compared to 2 years data. So maybe this transfer learning and augmentation cannot help. And next is the performance of Boolean segmentation use YOLO 11 segmentation model. And we performed the same model training process on YOLO 11 seg. And it can be seen from the table that the YOLO 11 seg outperformed the YOLO V8 on bruising segmentation, and we can see the best model achieved on 3-year data is close to 0.94, and the previous is 0.92. And here another interesting thing is that the transfer learning improved the performance here on 2 years data, but the augmentation slightly reduced the MAP 0.5. And augmentation slightly increased the MAP 0.5 here compared to this, while transfer learning didn't. And here are some results of bruising segmentation results. The first column is the ground truth, and the second column represents the result of YOLO V8 seg, and the third row represents the result of YOLO 11 seg. And we can see this sample. The bruising area of YOLO V8 is not very accurate because this part, the right part, is missing compared to the ground truth, but YOLO 11 predicted it correctly. And for this case, this is also be treated as the bruising area, but actually they are not. So YOLO 11 seg performed better than YOLO V8 seg. So we use YOLO 11 seg to extract the bruising area for further analysis. And to evaluate the accuracy of calculated the bruising ratio, we also calculate the bruising ratios from the annotations and use them as the ground truth for comparison. These two figures show the comparison results, and we can see the R square of YOLO V8 is around 0.55, and for YOLO 11, the R square is around 0.69. The result, I think, is consistent with the evaluation results I mentioned before. And we also calculate the MAP of YOLO 11 seg, which is about 16%. After that, we performed the developed approach on all images collected in 3 years and calculate the bruising ratio of each sample. The figure is massive, but we still can find some because it has over 50 cultivars. And this figure illustrates the bruising ratios among different cultivars in 3 years. And we can see many cultivars show similar bruising ratios among 3 years, although some cultivars may have huge difference. I think this may be because of the harvesting time or other facts. And then we further analyze the mean bruising ratio among cultivars. And here we use k-means clustering algorithms to obtain 2 clusters. And we want to distinguish the bruise resistant and the bruise susceptible cultivars. And we also did the t-test between the 2 clusters obtained by the clustering methods. And we can see in this table, the p-value is less than 0.05, which means there's a significant difference between 2 clusters. And after analyzing the clusters over 3 years, we find there's a similar threshold of mean bruising ratio between 2 clusters, and we can see here it seems like there's a threshold around 0.22 here to separate these two clusters. Yeah, here. And so we think the mean bruising ratio of about 0.22 could be an index that can be used to distinguish the bruise resistant and the bruise susceptible cultivars. Furthermore, we also did the linear regression between the mean bruising ratio and the Young's modulus. And all 3-year data exhibited a similar trend. Berries with a higher Young's modulus tend to have higher firmness and more resistant to mechanical bruising. So the bruising ratio is smaller. And the R-square is not very high here, so the correlation is moderate between the mean bruising ratio and the Young's modulus. But here the fitted function is very similar here. And we also develop a web page that can process the images and calculate the bruising ratio automatically. And this video shows how it works. First, we need to upload the image here and click submit. And then the developer approach will automatically run and to process the images. And then we can see the processed results. The green part shows the non-bruising areas, and the red part is the bruised area. And the calculated bruising ratio is shown on the bounding box. And there's also a table that recorded all the bruising ratios of each sample here. And there's another case of a cultivar with a higher bruising ratio. And here, the processing time is less than 5 seconds, I think. And we want to further improve it. Yeah, this is another case that have higher bruising ratios. And this is the bruising ratio. So in conclusion, the trend YOLO V8 and the YOLO V8 seg performed well on blueberry fruit detection and segmentation. The trend YOLO 11 seg outperformed the YOLO V8 seg on blueberry internal bruising segmentation. And the proposed DL deep learning-based approach is accurate compared to the ground truth. And the mean bruising ratio of about 0.22 could be used to distinguish the bruise resistant and the bruise susceptible genotypes. And the mean bruising ratio showed a moderate correlation with Young's modulus. Finally, I would like to thank USDA and IFI for funding this project. And I also would like to thank our collaborators, Dr. Perkins, Bates, Dr. Rizzo, and Hudak for preparing samples and measuring Young's modulus. Also thank Dr. Fumi Takeda for helping determine the mechanical bruising, and Dr. Rishi for helping analyze some data. Okay, that's all my presentation today. Thank you for your attention. If you have any questions, please feel free to ask.
Great, thank you, Dr. Tan, for your presentation. If you have any questions, since we are a small group, you feel free to unmute yourself and ask the question. If you want to type it on the chat, I'll happy to read it as well. I'm going to get it started because I have a question. So you show that sort of like the threshold for separating some cultivars that could be tolerant to bruising versus those that are sensitive was about 0.22. That is only under the assumption that to produce that bruising, you would have to use exactly the same technique as it was used by your collaborators in North Carolina, or if the bruising has been produced in any other way for testing cultivars, that 0.22 would also be the threshold for separating tolerant cultivars from very sensitive cultivars?
Thank you for your question. I think this is a good question. Currently, I think this threshold is only suitable for the same setup. Like we need to cut the cut cut the berries into halves, and then use our developed method to detect those bruising areas and calculate the bruising ratio. I'm not sure if this can extend to the common bruised fruits. So maybe we need to further test our algorithms, and we also want to release make our developed web page public, and more people can test it, and then we may get some feedbacks to see if this method can be suitable for other different cases.
Right. Thank you. Do we have more questions?
Hi. Hey,
Hello.
Amaya, just a question here. So
Go
thank
ahead.
you for the presentation. Very, very good. I see the use of the tree data seems to start to work much better now. Is there a way to this method of bruising? This one only apply if you cut the berry. This method doesn't work for if the berry you have the whole berry, correct? Or it does work?
Yeah, currently I think this method only suitable for those cutted berries, because I think it's hard to directly find those bruised areas if we don't cut the berries. Although it may have some rotten part or on the skin, but currently we think it's not. It's hard to directly detect the bruising area from the skin, so we need to cut them in half.
Okay. Thank you.
You're welcome.
So basically, anybody that wants to use this to phenotype for bruising sensitivity, they would have to follow exactly the same protocol that was used to develop. There's you couldn't change anything if you wanted to use the system as it is right now.
Yes, I think at least the berries need to be cut in half. Yeah.
Great, thank you. Do we have any more questions? So I'll just, there's a comment in the chat that we will be sending a short survey. If you could please respond to it, we would greatly appreciate to get some feedback. One more question from me. When do you think this is going to be available for researchers to use it? You said you were trying to develop a website.
Yeah, I think we are on the way to release the website, and I think currently we have deployed on our local computer. Maybe maybe at the end of this year, or at the early of next year, we can release our website, release this application for others.
Great, thank you. Last chance to ask any questions, Dr. Tang, about his presentation. All right, well, if nobody else has any more questions, thank you, Dr. Tang, for sharing with us your research. We really appreciate it. I think it's a very interesting tool and useful tool. We will be having another webinar in November. So if you are interested in attending, our next webinar will be in November 20. It will be about developing a new methodology for evaluating textures in cranberry fruit. And if you want to register, you can just use that QR code and it will take you directly to the registration page. So with that, thank you very much, everybody, for attending.
Thank you, everyone.
Hope to see you in our next VacCAP webinar.